Welcome to The Explainer, where we break down big ideas. Today, we're going to talk about a pretty radical new way to protect our mightiest structures from their oldest enemy, the wind. It's an idea that honestly challenges a century of engineering, suggesting the answer isn't more brute force, but a smarter, simpler solution that's been hiding in plain sight this whole time.
Okay, let's just dive right into this, because it sounds a little weird, doesn't it? But trust me, the physics behind a wobbly baby bouncer holds the key to both a bridge's greatest weakness and, according to our source material, its potential salvation. Stick with me, because this simple analogy is about to make a whole lot of sense.
So, to really get why this new solution is such a game changer, we first need to appreciate the sheer scale of the problem, a danger that has, and I mean this quite literally, haunted engineers for decades.
I'm sure we've all seen that famous, absolutely terrifying footage of the Tacoma Narrows Bridge twisting itself apart back in 1940. That wasn't just some freak accident. It was a powerful demonstration of a fundamental challenge that engineers still face today. These beautiful, elegant structures are incredibly sensitive to the wind.
It all comes down to this thing called resonance. Think of it like pushing someone on a swing. If you time your pushes just right, you don't even have to push hard. You can send them soaring higher and higher. Well, the exact same thing happens with a bridge. Small, steady gusts of wind can build up into these huge, uncontrollable movements that threaten the entire structure.
So how have we been trying to fight this immense force of nature until now? Well, for the most part, the traditional methods have all been about one thing: brute force.
For decades, the answer has basically been to just throw more steel at the problem. You either use these massive steel trusses, that crisscross scaffolding you see on older bridges, to make them stiffer, or you use huge external tension cables to try and brace the bridge against the wind.
But here's the fundamental flaw. These methods are kind of like trying to stop a flood with a leaky wall. They only dampen the vibrations, they soften the blow, but they don't get rid of it. And because their stabilizing forces run parallel to the bridge deck, they actually end up swinging right along with it instead of fighting against the motion.
And this is where the old way really shows its limits. Get this. The source material points to the Akashi-Kaikyo Bridge in Japan, one of the most heavily reinforced bridges on the planet. Even with all that steel, calculations showed that in a major hurricane it could still sway over 22 meters. That's more than 70 feet. The brute force method just isn't enough.
And this is where the whole story flips on its head. The source material we're looking at introduces a complete paradigm shift, a totally new way of thinking about the problem, by challenging the basic assumptions engineers have been working with all along.
For 100 years, engineers have been looking up, piling more and more structure above the roadway to try and hold it in place. This inventor had a breakthrough. The real answer was to look down and use the most stable part of the bridge against itself, its own feet.
So this shift in perspective leads to a completely new philosophy. The goal isn't just to absorb the energy, like a shock absorber. The goal is to actively eliminate the vibration the very moment it begins, by using an immediate and opposite force.
The key to this whole invention is a simple but incredibly powerful concept called counterforce. And to really get our heads around it, the source gives us a couple of just brilliant analogies.
Okay, first, picture a wrestler. To get total control, they don't just push back against their opponent, right? They use a diagonal, cross-body hold. Why? Because that specific shape locks down their opponent's ability to swing or twist in any direction. It completely neutralizes them.
And that brings us right back to our opening question about the wobbly baby bouncer. As it turns out, that bouncer stops moving instantly if you just take a string and connect its feet diagonally, in a cross shape. The feet start working against each other, completely canceling out any wobble.
And that is the exact same principle that's applied to the bridge. So here's how it works. First, steel ropes connect the roadway down to the base of its own pylons, in that all-important cross shape. So when the wind pushes the bridge deck to the left, the ropes on the right side instantly tighten up. This creates that immediate counterforce, which pulls the bridge back to the center and just erases the sway before it can even start. And it works the same in reverse, stopping all that back and forth movement dead in its tracks.
So you see the key difference here. The old systems, they use these parallel forces. They just end up moving along with the bridge as it sways. They might reduce the swaying a bit, but they don't stop it.
But this new system creates a cross-shaped counterforce. The forces are now actively fighting each other. One side pulls against the other, creating this perfect state of equilibrium that cancels out any movement before it can build into something dangerous.
The inventor describes this whole system with one more really elegant analogy that I think perfectly captures its efficiency and, well, its genius.
Think about it. Your seatbelt does absolutely nothing 99.9% of the time, right? It's just sitting there, completely passive, not putting any stress on you or the car. But the moment there's a sudden movement, it locks up instantly. This system is the exact same. The ropes are only under tension when the bridge tries to move, acting like an instant dynamic brake.
And so, this very elegant idea leads to a whole cascade of real-world benefits. It's way lighter, so you don't have all that massive self-loading weight. It's simpler and cheaper to install and maintain. And because it's so much more effective, it could let us build wider, more robust bridges, maybe even bridges capable of carrying heavy loads like trains.
Of course, no single engineering solution is ever perfect. There are always trade-offs, and it's important we understand the potential limitations here.
Yeah, the patent is actually very upfront about the main drawback. This network of cables running under the bridge could potentially get in the way of shipping channels, especially for really tall ships. But the source does note that there are different versions of the design that can help mitigate this issue, depending on the location.
But here's what you should really take away from all this. It's the power of a fresh perspective. For almost 100 years, engineers looked up to solve this problem, just piling on more and more steel. The breakthrough only came when someone decided to look down.
And really, that leaves us with a final thought to chew on. What other complex, seemingly impossible challenges might have a simple, elegant solution hiding in plain sight, just waiting for us to look at them from a completely new angle?